Good morning, everybody, and welcome to a webinar on building real-time inference AI services with FIWARE. I'm Rihab Feki. I'm a machine learning engineer and evangelist at FIWARE, and I'm going to be presenting for you today's webinar. So to start, let's have a look into our learning goals, and at the same time, we can have an overview at what we're going to cover throughout this presentation. So first, we're going to learn what real-time inference is. Second, we're going to learn how to manage and exchange data in real time with the context broker. We're going to learn how to train a machine learning model with historical data. And here we have a practical part. We're going to learn how to create a Python ML package and why we should create it. Our two last points are serving a machine learning model via REST API with fast API. And last but not least, we're going to have a demo, and I'm going to show like the implementation of the end-to-end real-time inference AI service. So without further ado, let's get started. And so what is real-time inference? Before I define what real-time inference is, I would like to first explain what inference is. And as you know, in every machine learning life cycle, we start with ingesting data, cleaning it, doing some experiments with different algorithms, and we train some machine learning models. Once we are satisfied with a model, we take it and deploy it to be used in production. And that model will be exposed to some real-world data in order to get predictions. But when is it real-time? Is this inference? It is when this process is triggered at any time and an immediate response is expected to get predictions. So this ML inference can be done in real time on individual records, such as with REST API endpoint, as an example. And there is one thing to point here, is that there is no point in training machine learning models if there is no plan to make them accessible for applications to use. So in this exercise, we're going to serve our machine learning model as a REST API for real-time inference. I'd like to first present our use case. So to have an overview, it's basically in the scope of agri-food. So we have a farm in which there are some animals and they are wearing some GPS collars. And the farm owner wants to predict or classify the animal activity based on the XYZ coordinates and the observed ambient temperature. So in this use case, we have three participants. The first is happy cattle. So this is the farm raising animals of different kinds. They have set up an IoT system and installed the farm management system that creates a digital twin of their animals in the farm. So now they want to extend its functionality to recognize the animal activity they are raising. For that, they will rely on Smart Shepherd, the AI service provider, which is going to be responsible for training and deploying machine learning model, as well as providing an interface for the data provisioning needed for the inference to get future predictions based on the right time data. As I said here, that the animal activity prediction will not only rely on the coordinates of the animal, but also on the ambient temperature. For that, there will be a third party, which is real-time weather, and it's a weather data provider operating weather measurement stations all over the world. Now that we have seen our participants, let's have a look at the overall architecture. So one thing to note here is that this architecture only covers the part of the inference. So it does not cover the data ingestion, the training, all the other steps. We assume here that our AI service is already having our pre-trained model, and we're only going to show the data flow for that real-time inference to happen. So what we could notice from our architecture, that there is one component which is in common between the three participants, which is the context broker. So the context broker is going to allow us to exchange data between the different participants, organizations, in real time, but most importantly, in a standard format following the NGSILD API. And since our goal is to have the inference happen in real time and in an automated way, we are going to rely on a mechanism offered by the context broker, which is the subscription. So the subscription is basically, it enables to get a notification in a particular endpoint on some attributes we want to subscribe to, so that whenever these attributes have an update or change, we get a notification of the new values of that attribute or these attributes. Yeah, so, and in our situation, we will need to do 3 subscriptions. So the first one will be that Smart Shepherd subscribes to Happy Cattle to receive notification for new animal coordinates. So it is explained by this arrow here. And thanks to this notification proxy, or the component called Apollo, it will enable us to translate the notification payload to creation of attributes, or to create like an attribute or update attributes if they exist in the context broker of the subscriber. So yeah, this is our first subscription. The second subscription will be that the AI service subscribe to its own context broker to receive a notification whenever there is a new animal coordinate. So this is due to the first subscription. And once it receives these animal coordinates, what we need to trigger the inference is the weather data. So the AI service will do a query for to real-time weather and get the ambient temperature in particular location. So once we have our data ready, the inference will be triggered, and then we will calculate the prediction of animal activity, and then the animal activity attribute is going to be updated in that case. So what we want is that Happy Cattle receives this prediction automatically in its context broker. And as you could expect, what we need for that is a third subscription. So Happy Cattle will subscribe to the context broker of Smart Shepherd to get notified whenever a new prediction is calculated. This is basically how this workflow is going to be repeated in an automated way, and it's always going to start whenever there are a new animal coordinates update in the context broker of Happy Cattle. So now that we've seen how the workflow works, I would like also to explain one more component in the architecture, which is the IAM. It stands for Identity and Access Management. So these are here like some components which you could add if you want to use this architecture in production. So it's recommended, but it's not going to be covered in our presentation today. But I recommend you to have a look in the FIWARE catalog if you want to find out more, especially that there will be an exchange of data between different organizations. So it makes sense to have it. Yes, so these slides basically represent what FIWARE generic enablers are used in our architecture. Not going to go through it because I already explained it. Also here, the 3 different subscriptions which we need to do for this real-time inference to happen, but you can check it out for reference in the future. Let's now move on to have an overview of the AI service. So as you know, Smart Shepherd is our AI service provider, and it's in its environment, we have a context broker through which we get the real-time data of the animal coordinates and the temperature. So there will be a first phase in this AI first service, which is the data pre-processing. So as you know, the data comes from the context broker in NGSILD format. And the first phase is to transform this data from NGSILD or JSON to a format which is suitable to our trained AI model. And once that step is done, we trigger the inference with our pre-trained model and to get the predictions. Then we have a post-processing phase to transform the prediction result or the output of the trained model to, again, NGSILD format so that we can update the prediction attribute, which is animal activity, in this case, in the context broker of Smart Shepherd. So this is a high-level overview of the AI service. And now I'd like to present the data set which we used for the training. So basically the features or the columns of this data set are the timestamp and the XYZ coordinates of the animal. Here temp stands for temperature, and our target column or our label, which is the animal activity. So let's have a look right now into the training notebook. And the different steps of training. So here there's a part which describes the data set, so which I already explained. Our target label or our possible animal activities which we trained the model on are that the animal could be walking or grazing, stand up or standing, lying, and etc. So the first phase is to import our libraries. So we're going to need libraries for data manipulation and plotting, like pandas, numpy, matplotlib. We're going to need libraries to split the data to a train and test set. We're going to need libraries for the pre-processing, for scaling and encoding our data. We're going to use a pipeline to do the training, and for that I'm importing a scikit-learn pipeline. And to save that pipeline, we need, as an example, joblib. And I'm going to use as a classifier XGBoost. And to check the performance of our model, we're going to use the classification report. So as my data set is saved in Google Drive, here I need to mount to my storage. And once that is done, so we load the data. My data set is in a CSV format, and its shape is like the following. We have almost 62,000 observations, and we have 6 columns, which you can see in here. So we can do a data analysis phase. We check if we have any null values in our data set. You can see that we don't have that, which is good. We can check some statistical analysis of our numeric features, so the mean and max and other characteristics. So one thing good to have an overview of is our label column distribution. So these are basically our, this is our label, our target column, and these are the like the proportions of our target class and how many observations we have for each class. And as you can see, it is a bit unbalanced. So, and yeah, we're going to see how we can train the model in a way that it is trained on all the on these classes. So the next phase is to label and code our target column. So since our target column is in string format, so we need to transform it to number. And we do that with the label encoder. And the next step is to split the data to a train and test set. And for this, I'm going to use a cross-validation and a particular stratified keyfold. And what it will enable us to do is to get stratified folds, which means that for the training, we're going to make sure that from each of these classes to get some samples which our model is going to be trained with. So we're going to make sure that the model is trained on each of these classes, and also that in the test set we have these 4 classes as well in our data. So that's basically the code for it. And these are the features we're gonna need. So we don't need the timestamp in this case, so only the animal coordinates and the temperature. And we're gonna create our pipeline. Doesn't have so many steps, just the standardization, like the scaling step and our classifier. And here, like some parameters for our classifier. Once we have our pipeline set up, we can do the training. So, and yeah, and once we do the training, we can save our model. And we can do like the evaluation. So in here, let's have a look at our predictions on the train set and on the test set. And it's a classification report. So for the train set, we have, we can take a look at the F1 score. So since our data is unbalanced, it makes sense to check it out. So for each of these target, our target classes, so for grazing 99%, stand up almost 90%. So the values are good of the F1 score. And for the test set, same. So our model works fine. And yeah, so this is basically like the training notebook. Yeah, now that we've seen this phase, so I'd like to say that Jupyter Notebooks are not ideal for production. So they are a great way of easily exploring the data, doing experiments, but they are not ideal for reproducibility, and they're also difficult to debug, and in short, not ideal for production. So that's why a better practice is to create a Python package for your ML solutions. And I'm gonna get later into to have an overview of the ML package and the source code. But before I get there, let's have a look at the structure of the ML package I created. So it's called a classification model. And under it, I have basically the following repos. So I have a config file in which I put all the parameters for my model, its parameters, the train test set, size. So instead of like hard coding things in our code, it makes sense to use config files. Here I have this repo for the data set in which I put my training and test sets. A repo for pre-processing. I have a data manager, just responsible for loading data and saving the model and doing some other functionalities. We're going to have here a training model repo. This is where we're going to save our model output and or trained models. And okay, our most important modules are the pipeline. So where we're going to put the different stages of our data NML pipeline, our so the training here, so and the predict module. This is to do the inference with our pre-trained model. I also have done some tests to test the prediction. This was a minimal thing to do. And yeah, that's basically the structure of my ML package. I would like to give you an overview of how it is. In here. So here under my Smart Shepherd folder, I have my ML package. This is my classification model folder, and I guess it makes sense to go through. First, I'm going to show the config file and what I have in it. So my package name, the names of my training and test data files. So my so the features, feature names, and some parameters of the train test split. So the test size, number of splits, the random seed, and some also parameters of my XGBoost model. This is very useful here to have a config file, because if you want to change your data, for example, if you want to add more features, you can easily configure or add it here. And same if you want to experiment with another model, you simply could add its parameters here, or if you even want to tweak this model and change its parameter, you can easily do it from this config file. Yeah, next I'm going to show the our pipeline. So, and as I showed in the Jupyter notebook, so we have a scaler and we have our classifier. And to do the training, so to run the training, what we need to have is to load our dataset, and we're gonna have our predictors and target columns. We're going to do the encoding of our label column, and we're going to do the step of the train test splitting with the stratified key fold. And once that is done, we do the training. So, and we can, as a last step, we save our pipeline. And it's going to be saved in the trained models folder. And no, so to do the prediction in the future, what we need to do is to import our pipeline and our encoder. And here to make predictions, we get our data, transform it in a data frame. We do some validation steps to check if our new data is fine, and then we do the prediction with our pipeline. And here our predictions results. So this is the prediction module. I guess that's it. What I can show also our requirements. So for the building the ML model, for testing and packaging, you could have a look into this. So I have linked the source code in the presentation. So now let's get back to our presentation. And yeah, now that we have had a look on our ML model package, our last step is the ML API. And as I said, we want to serve our machine learning model via REST API. And here's now an overview of the ML API architecture. So our client will do a post request on our notification endpoint, and that's going to start a pre-processing phase, and then a prediction, and then we're going to have to do the post-processing to get the results. And in our ML API, our ML model package is included as a dependency in here. So yeah, I would like to also show you the ML API source code, so to have a better understanding how it is implemented. But before that, so I have here so my so API documentation. I have here like health tech, health endpoint, but most importantly our prediction endpoint. So here I included like some a test record to test our trained model, and we can try it out to see if it works. So you can even change here, you know, value 7 to 4, make this 23 degrees, and I can execute. And we get our prediction in this format. So this is our response from the trained model, and based on these coordinates, we see that the animal is sternal lying. Yeah, but for our automated inference, we have our notification endpoint. This is where our notification from the context broker are going to be received. And let me show you at least the code behind it. So I have here my ML API, and here are my endpoints. I've just showed the predict, but we are interested right now in the notification endpoint. So what we have here is basically like the step to parse the notification, to get the animal coordinates and the ID of the animal. And once that is done, we do a query to real-time weather to get the temperature data. And now that we have our coordinates data and temperature data, we prepare so the model input attributes or features with this step, and then we can make our predictions. So from our classification model here, it is imported. Once we have our results calculated, we do our post-processing phase to transform our data to NGSILD, and then we're going to update the predictions in the context broker of Smart Shepherd. And this is basically my notification endpoint. So to summarize, I would like to get through the implementation steps. So first, what I've done is the data exploration and the ML model training. You can find the notebook here. I created the Python ML package for the classification model, and it includes the processing, training pipeline modules, and prediction module. I implemented the ML API based on Fast API for the inference. And we set up the environment of each participant with Docker, actually Docker Compose, since we have different components. And last but not least, so we're going to set up the predictions so to do the real-time inference and the real-time data exchange. Now I'd like to show a demo of how this inference works. So, yeah. Okay. Basically, I have uploaded this all the source code to GitHub, and I have included here all the different steps, so which we need to perform to set up the whole architecture and basically like the Docker setup for each of the participants. And you can have a look at the repo afterwards. I've already done the Docker setup. So what we need to do right now is to do the subscriptions. So as I showed earlier, our 3 subscriptions. So from Smart Shepherd to Happy Cattle, from the AI service to its context broker, and then Happy Cattle to Smart Shepherd to get the prediction. So I'm gonna get to do that right now with you. So in our terminal, I simply copy this subscription it is created. Okay, let me also explain it. So basically this first subscription, Smart Shepherd subscribes to the context broker of Happy Cattle to receive in an automated way animal coordinates updates in its context broker by means of a notification proxy. So the endpoint of this subscription is the notification proxy, or Apollo, and the attributes which we want to have like update on are the locations. So, and entity of type animal. So this is it, our first subscription. And our second subscription is a Smart Shepherd AI service subscribes to its own context broker in its own environment to receive the notification at the notification endpoint, the coordinates, once it is updated to the subscription one. And that will trigger the calculation of predictions, which are also relies on getting temperature data. But yeah, that's another detail. So let's do the second subscription. And it is also created. And our third subscription, it is basically, so the attribute we're subscribing to, or so Happy Cattle subscribes to get the animal activity. And yeah. Hope it is visible. So it is also created. And okay, now here we have an example of usage. So I create, so we're going to simulate everything since I do not have an IoT system set up and so on. So I'm going to create first a temperature sensor entity, and I'm going to add some temperature data. And this is how I'm going to do it. Okay, now we have it. It is created. And the second step is that we create an animal entity at the context broker of Happy Cattle. So, okay, do that. So this is the data and how it looks like. So our animal is a cow, and it is in these coordinates. So it is also created. So at this stage, the only Happy Cattle has like the data in its context broker. But since we already have set up the subscriptions, if we query Smart Shepherd, we should now find these same coordinates in its context broker. So let's do a GET request and find out if our subscriptions work fine. So yes, great. So we can find here our attributes, our coordinates, sorry, in the context broker of Smart Shepherd. This is due to the subscription. And now, if Smart Shepherd gets the animal coordinates, logically what should happen is that the AI inference is triggered. And if we check our context broker of Happy Cattle, okay, first let's update Happy Cattle context broker. It's done. And what we need to do right now is to check the context broker of Happy Cattle, and we should get there the animal activity attribute. All right, yes, here we go. We got it. So you can see that this animal activity attribute is being created in or updated in the context broker of Happy Cattle without us creating it. So the inference has happened with our new attributes. So yeah, this is basically it. And I would like to show here. So I linked all the resources. So to the source code, the data sets I used for the training notebook, some links on how to create a Python package, and documentation of FAST API, some other useful resources of NGSILD subscriptions. There are the tutorials here, and yeah, other components which I used for this architecture. Guess that's it from my side, and thank you for joining, and I hope this was useful and that you learned already from this webinar. And if you have any questions, please feel free to put them in the chat, and yeah, I'll be responding to them gladly.